Okay, so hello everyone. Thank you very much for coming. If you're hungry, please help yourself to some biscuits at the back. It is my great pleasure to introduce our first speaker today, Roberta Amato. Sorry, I hope I pronounced it correctly. Obtained her PhD in physics in 2021 through a co-tutor program between the University of Palermo in Italy and the University of Tübingen in Germany. She subsequently held a postdoctoral position at the Institute of Research of Astrophysics and Planetology, or IRAP, in Toulouse in France, where she was also a member of the XMM Newton 30 Science Center. In 2023, she moved to the Astronomical Observatory in Rome, where she's currently based. Her research focuses on the analysis of X-ray data from X-ray binary systems, with particular emphasis on the spectrum and temporal properties of ultraluminous X-ray sources. So we'll also have a talk on ULXs next week, so please listen carefully. So take it away. Thank you very much for coming, Doris.
Thank you. Do you hear me? Yeah, okay. Thank you for the introduction and thank you for having me. This is true, you will have another talk on ULXs next week. So it's convenient because I will do a little bit of a generic introduction and then I will discuss one of the latest results I obtained with my collaborators, because in particular, we decided to adopt some novel artificial intelligence approach to try to understand the physics and the characteristics of the sources. So when I introduce ULXs, I like to show this beautiful image. This is a composite image of the galaxy M51, which is the bigger one, and M52, which is the smaller interacting galaxy. It combines optical image taken with the Hubble Space Telescope and an X-ray image taken with Chandra. So there are a few characteristics of this galaxy that are quite striking. First of all, the central AGN, active galactic nucleus, which is super bright. Then you also see the structures of the arms of the galaxy with a lot of dust, star-forming regions, and so on and so forth. And all the little purple dots that you see, those are all X-ray binaries belonging to the galaxy, and some of them are extremely bright, extremely luminous, almost as much as the central compact object. So those are what we define ultraluminous X-ray sources, or ULXs. They are point-like extragalactic off-nuclear X-ray sources with a luminosity higher than 10 to the 39 erg per second, which is the Eddington limit of a black hole of 10 solar masses. So the idea is that they're not extended, they are not in the center of the galaxy, so not to be confused with the central AGN, of nuclear, and they are found mostly in other galaxies, with an asterisk because there is some discussion going on if we have ULXs in our galaxy. I will not talk about this, I'm happy to discuss this with you later. So why this luminosity threshold? The reasons are historical, because if you recall the formula of the Eddington limit, you can obtain it assuming that there is an isotropic accretion onto a spherical compact object, and in the equilibrium, the force of gravity and the radiation pressure are equal to each other, and then you derive this maximum achievable luminosity, the so-called Eddington luminosity. In the specific case of an accreting compact object, you can substitute the formula for the opacity, and you have this Eddington limit, which is roughly 10 to the 38 erg per second times the mass of the compact object in unit of solar masses. So I don't have to explain you any further, but if you have a neutron star as your accreting compact object, neutron star has a mass of 1.4 solar masses roughly, so your Eddington luminosity is of the order of 10 to the 38 erg per second. For a 10 solar masses black hole, the Eddington luminosity is of the order of 10 to the 39 erg per second. So when in the 80s people started discovering ULXs, they thought, okay, these are very, very bright, above 10 to the 39 erg per second, so we found intermediate mass black holes with a mass range between 10 to the 2 and 10 to the 5 solar masses. However, in 2014, coherent pulsations were discovered from one ULX, M82X2, and if there is a coherent pulsation, it means that the compact object has to have a solid surface. If it has a solid surface, it's a neutron star. For a neutron star, the Eddington limit is 10 to the 38 erg per second. These sources are way, way brighter. So we are entering effectively the regime of super-Eddington accretion. This is the plot of the discovery paper, Baghetti and collaborators on Nature, and this is just to show the transient nature of the sources. So after since 2014, we know overall 2000 ULXs so far, but the pulsations have been found only in a bunch of them, I would say roughly 10 sources. And this introduces a series of problems. First of all, knowing the nature of the compact objects. Now, finding the pulsations per se, it's a really, really tricky business, I would say, because these sources are transient. They need very long exposures because they are in faraway galaxies. So I'm talking hundreds of kiloseconds of maximum Newton observations, for instance. And then to find pulsation, you have to correct for strong Doppler modulation and extreme spin derivative. Here I show you two examples. One is NGC 5907 ULX1. So if you perform a simple fast Fourier transformation and you look for the signal, you rarely find it. But then if you apply correction for the Doppler modulation, then you have a very significant pulse signal. The other example is NGC 1313X2, where pulsations have been found only in 3 subintervals of the whole observations. So it's really, I would say, a delicate analysis to do. What else do we know about ULXs? Apart from the spin pulsations, they show orbital and superorbital period. They have hints of bimodal distribution, suggesting some sort of alternation between the propeller effect or not. They have millihertz QPOs. So to put together all these temporal behavior, the idea is that the precession, the accretion disk is actually precessing. People talk about lens steering precession or magnetic-driven precession. I will not go into the details because I don't have time, but if you're curious, we can discuss about this later. If we move into spectra, this is a collection of spectra from several sources, and I challenge you to find the two spectra that are exactly the same in spectral shape or intensity. They vary a lot. With time, people found that there are actually 3 main categories. We talk about hard and soft ultraluminous X-ray sources or hard and soft ultraluminous regime. If you have mostly X-rays above or below 2 keV respectively, with the category of the super soft ultraluminous X-ray sources, which have little to none emission above 1 keV. And then, if you can see, there is this characteristic curvature, typically between 2 and 5 keV. If the curvature is not present, then we have this broadened disk state. Okay. Typically, the spectral model using 2 components. Sometimes there is a high energy cutoff, so I need a third component. Sometimes there are smaller residuals at 1 keV, which can be explored in a better way in high resolution spectra of ULXs, and they are associated with disk outflows. It will be clear in a moment. And then often they do not stay in the same state, but they transition from a state to another. So to put all these things together, spectral and temporal properties, we need to dive into the theory of super-Eddington accretion. So the idea is that if you have a very high mass transfer rate and your sources are creating very high rates, then the radiation pressure starts to dominate and overcome the force of gravity. So what happens is that your radiation pressure starts to push the matter outward, and not on the compact object itself. So the disk starts to behave differently from a classical Shapura-Sunyaev geometrically thin disk, and it starts to be puffed up. And then at the same time, the radiation pressure is so high that it starts to launch winds from the surface of the accretion disk. And the winds are so high, they develop in high Olsen velocity that they form this kind of wind cone, so that your radiation is basically confined. We talk about beaming, which is not Doppler boosting or Doppler beaming. This is just a geometrical collimation. So this is a sketch that I did myself to have like a representation of the system. You have your compact object on the inside. It might be a neutron star or a black hole. The radiation pressure pushes the disk so that the disk starts to be puffed up to a characteristic radius, which is called the spherization radius. And the winds are launched from the surface of the disk. So depending on the inclination of your system, you can assess the innermost regions or the outermost regions. In the innermost regions, so if you see your system face on, the innermost regions are hotter and they are responsible for the production of the harder X-rays. So you are in the hard ultraluminous regime. While if you start to move towards systems that are more and more adjoined, you start to intercept more of the winds, which of course shield a little bit the radiation coming from the innermost regions. And then you also intercept more of the outermost parts of the accretion disk, which emit soft and eventually super soft ULXs. So the spectral phenomenology that we observe in ULXs actually depends mostly on the inclination of the source. And you have a little sketch in this column. While this is a snapshot of a simulation of a super-Eddington accretion flow onto a 10 solar mass black hole. And I like to show it because it gives you an idea of how extremely clumpy, chaotic, and variable with time is the wind. So when I'm talking of disk outflows, this is the picture that I have in mind. And these winds reach relativistic velocity. We're talking 30–40% of the speed of light. All right, is that all? Of course not. The community is actually discussing heavily if this is what is there to the super-Eddington accretion, and in particular there are two schools of thoughts. One is claiming that we see such high luminosity because the signal must be highly beamed, while the other school of thought is saying that actually the magnetic field must play a significant role. And why I'm telling you this? Because in the first case, if you have a beamed emission, remember, beaming is, for me, geometrical confinement of the radiation coming from the innermost regions. So if you have a beamed emission, the luminosity that you observe is actually scaled. It's the true luminosity scaled by a factor 1/b, where b is the so-called beaming factor, and it's much, much less than 1. So your observed luminosity is way higher than the true luminosity of the source, also because the Eddington luminosity assume isotropic accretion, while we're not in an isotropic situation anymore. The other school is actually saying that we have to consider the magnetic field in the source. And in presence of a high magnetic field, the electron scattering cross-section is reduced, so that the Eddington formula can be rewritten in this way: 2 times the Eddington limit times the magnetic field to the 4/3. So at least you have a factor of 2 of difference depending on the magnetic field. There are pros and cons with both schools. If you assume the strongly beamed emission, then you cannot explain the pulsations that you see and the fact that they are extremely sinusoidal. If you assume high magnetic field, then you should enter at some point the propeller regime and somehow alter the accretion, or at least not be able to have such high spin derivatives. So to put things together, the suggestion is that actually the bipolar magnetic field is mild, 10 to the 11, 10 to the 10 Gauss, but closer to the surface, if the compact object is a neutron star, you have higher magnetic field, 10 to the 14 Gauss, and it's a quadrupolar component. And then if you assume a mild beaming, then you could, in principle, explain the phenomenology of these sources. This, of course, raises the question, are all ULXs and neutron star ULXs? Well, the simple exploration that we can do is to look for pulsations. Are pulsations detected? Yes, the source is a neutron star. Are pulsations not detected? Well, in this case, we can't really discriminate if the compact object is a black hole or a neutron star. We can exclude neither of the two scenarios. And this is why we decided to use artificial intelligence, and in particular clustering, to see if we can separate the two different populations of neutron star and black hole ULXs. This is a work that I did in tight collaboration with Niccolò Pinciroli-Vago, who now graduated from the Polytechnic of Milan. He was a student of informatics, and he was also a visitor here for quite some months, so you probably saw him around. So what we did, we decided to collect all information available on ULXs, build a database, applying a clustering method, and then see if the two populations are well distinguished, well separated. To produce the database, we used available ULX catalogs, and we complemented the information of the catalogs with information for the XMM Newton catalog. I will not go into too much details. I want to just stress that the clustering is a non-supervised machine learning method. So we use the labels to check a posteriori if our source were pulsating ULXs, if they show pulsations or QPOs. Bear in mind that in this database, each entry is an observation. So we have like a giant database of XMM Newton observations of pulsating ULXs, of ULXs in general. So as a machine learning method, we decided to use Gaussian mixture models because they allow to derive a probabilistic association of or membership of each observation to the right cluster. Again, I will not go into too many details here, but the idea is that each cluster is Gaussian shaped, and the observations belonging to each cluster have a Gaussian probability associated to it. And then we perform the analysis. So I show here a few results, and I will take a few minutes to guide you through this plot. The algorithm, of course, is acting in an n-dimensional space, which is not understandable to the human mind, so we give you a 2D representation. You have in the x-axis, in the y-axis, the broadband flux, in the XMM Newton band from 0.2 to 12 kV, and then in the y-axis, the flux in the hard band from 4.5 to 12 kV. Now, the blue dots mark the observations of ULXs, which belong in the cluster where the majority of the pulsating ULXs ended up. So we have a blue cluster, which is mostly contains pulsating ULXs. And then we have a red cluster, where are all the other observations of other ULXs. In this plot, the black circles, mark those sources that we know for sure are pulsating ULXs because we detected the pulsation, so we know it's a neutron star. And we found that all sources we know a neutron star ended up in the same cluster, blue dots. So each circle point is a blue point. Plus, we found other blue points which are not known ULXs, which ended up in the same cluster of the pulsating ones. So the idea is that these not marked blue points are potentially very, very good candidates to go and look for pulsations. We found 85 of these candidates for 355 observations, and this provides a list of XMM Newton observations where to go to look for pulsation, to use to ask for new observational campaigns, and so on and so forth. We also produce the decision trees, which is a kind of a roadmap. So if you have new observations and you want to have a feeling if this is more likely a pulsating ULXs or a non-pulsating ULXs, you can just follow the branch of the trees and find out which cluster is most likely your source belongs to. Is that all? No, unfortunately, because we found a few biases and a few issues with the XMM catalog. The first being that the fluxes, the hardness ratios computed in the XMM catalogs assumed a fixed power law model with fixed NH and fixed gamma. So the only thing that changes is the normalization. And as you can see from this plot, a simple power law is not representative at all of ULXs spectra. It's not a good fit. So what we did to improve on this work, we fitted all available XMM spectra with more reasonable models. We derived the best fit parameters, the unabsorbed flux, luminosity, etc. And we produced a new database with much more parameters. Here in this plot, I give you a comparison of the, this is an hardness luminosity diagram. So you have the hardness ratio in certain energy bands over the luminosity. And those are all unabsorbed, which is an improvement with respect to the XMM Newton catalog. In blue, you have the results of the fit that we did, and in orange, the results from the catalog. And as you can see, there is a different distribution both in luminosity as in hardness, because now we are accounting for the absorption. So we give them to the same clustering algorithm, and the results this time were not so good, because we found, for instance, that some pulsating ULXs, observations of pulsating ULXs, were associated to the wrong cluster. You have here a very clear example. But we found that at least one observation of each pulsating ULXs is associated to the correct cluster. And this is what, sorry, I pointed to the wrong one. So these are the bad examples. But as I was saying, at least one observation for each pulse was associated to the correct cluster, and this is a success because once you identified one observation, then you have you can assume that that is true also for the others. What are the next steps? We want to expand the database as much as we can. So the idea is that we want to include X-ray data from other satellites, Chandra, Nuster, NICER, all the X-ray observations that are available. We want to complement them with multi-wavelength information, so using other catalogs, other missions. We want to use optical to see if there are information about the optical counterparts, nebulae, bubbles around ULXs, and so on and so forth. We want to use information about the galaxy, so metallicity, star forming rate, the type of galaxy. The idea is to make a database as huge as possible so that the machine learning methodology that we're using can have a complete view of the system and eventually derive the physics for ultraluminous X-ray sources. So I stop here. These are my conclusions. Why we need to study ULXs, because they are the closest, like in terms of distance, sample to study super-Eddington accretion. Though we know the basics of the physics of super-Eddington accretion, we actually have some open questions which are very, very relevant. First and foremost, the nature of the compact objects, and we hope that AI-based methods can help find new solutions to this problem. And for doing that, we need to produce a more accurate and complete data set. I want to advertise that we are going to have a symposium at the next European Astronomical Society meeting, which is going to be at the end of June, between June and July, in Lausanne. So if you are planning to attend the EAS, please stop by our symposium, which is going to be on Monday and Tuesday. And I think I will stop here.
What I think you said in one of the first slides that we only know about 10 pulsating ULXs, but it looks like you have many more.
No, you're referring to this plot, for instance.
Right, or the other one, yeah.
Yeah, because here each data point is an observation, not a source. So pulsating ULXs have been observed many, many times.
Oh, I see. Okay.
One of these. So, each point is an observation.
An observation. Okay.
Yeah.
And the second question I had in your big database. So I understand because then you show spectra. So you have a lot of information. You have spectra, luminosity, and everything else anything that comes from the XMM catalog, correct?
Correct, or from the spectral fits that I performed.
Oh, in after,
Yeah,
in the second
yeah,
round. Okay, thank you.
No problem.
Any other questions?
Hi, nice talk. I would agree with you that probably the majority of ULXs are super-accreting sources. There's this new evidence is fantastic, and also stuff we saw earlier in terms of luminosity functional X-ray sources, stuff like that. What is your feeling now about the old-fashioned ULXs? I mean, are there intermediate mass black holes in the sample left?
I believe so. Yes, I believe so. Because I did some analysis on some hyperluminous X-ray sources, so I'm talking 10 to the 41 erg per second or above. And if you look at the spectra or at the hardness, some of them are very soft, like with a gamma of 4, and have nothing to do with the population of ULXs as we know it. So I'm convinced that there are other phenomena like tidal disruption events or accreting intermediate mass black holes in the whole population of ULXs. So my answer is yes. Probably some of them, especially the most luminous ones, are still very good candidates for intermediate mass black holes.
Is there any, what's the fraction, I don't know if you can say that, of the sample, how many would be intermediate mass black holes?
Less than 10%.
10%, so it's
yeah, just a few, yeah.
Okay.
Hi, nice talk. You didn't mention the features you used to train the model, the mixture model. So, and how do you pick the feature? How many of those was the, and have you considered, just a second question, have you considered adding another cluster? So I understand that the problem is dual, so either pulsating or not pulsating, but.
Okay, so for the first question, not an expert on artificial intelligence, but the Gaussian mixture model is unsupervised. So we don't need to train. We did some PCA analysis just to determine the better parameters, but we didn't train the algorithm. And so for your second question, yes, we consider actually the possibility of using other cluster algorithms and to let the number of cluster free, so that we see if there are subpopulations. We thought about it, we didn't do the analysis, but it's a nice suggestion, yeah. If, I don't know, at least there might be a third cluster which can account for all contaminants, for example, yeah.
One final question.
Thank you. This is a very interesting talk. I'm just wondering about the statistical biases, which, in this plot, can you actually detect periodicity for the sources which are faint versus the sources which are very bright and luminous? Because then, if you cannot, then you can account for the bias like that in your models.
We accounted for the bias, or at least we discussed the bias in the paper. One extremely evident bias is that usually pulsating ULXs have more observations, because once we know the pulse, of course, we ask for more observations. So there is a bias toward this type of observations indeed. Yeah, another bias is that if they're too faint, we do not detect them. And the third bias would be that usually the pulsating ones are the brightest and the hardest. So everything is kind of shift, but I think it's the best we can do with the data that we have. So yeah.
Yes, of course, but can you include also simulations and trying to understand what is the limit for detecting pulsations? But then you could include it in your analysis.
We could, yes, in principle, yeah. Like I don't know, this bootstrapping techniques.
Something to allow you to understand, the limitation of the sample.
Yeah, it's something. Yeah, we will consider it. Thank you.
Great. Okay, thank you. Let's thank Roberta. what we make our change speaker. I'm very pleased.
Okay, good.
You're unmuted on Zoom.
Yeah, okay. The camera.
Yeah, that's fine.
Oh, it's fine. Okay, perfect.
Yeah.
Nice. Okay, then I can just share.
Just share the screen.
Okay, so. Okay.
Wait, can you share the screen?
Also. My bad. Okay, share. And now. Okay, ready. Okay, well, thank you, and it's a pleasure for me to be here, and thanks to the organizer for giving me the opportunity to speak here today. So I want to tell you a few details about the model, the project I've been working on in the last few months, and I hope to get your thoughts, feedback, and questions on the project. It is very much a work in progress, but I want to start with the motivation for this project, and in particular with this plot, which is showing essentially the masses that we're measuring for quasars at high redshift. We're measuring these extremely large masses of like 10 to the 9 solar mass or so. And you know that if we assume that these quasars accrete like at the Eddington limit or some fraction of the Eddington limit, then we have this exponential growth of black hole mass with time. And so what people do usually is essentially start from these 10 to the 9 solar masses that we measure here and draw this exponential line until we get to the very high redshifts, and we start talking about the seeds, so about the first black holes that actually formed in the universe, and how we can learn about these first black holes essentially from this scaling. Now, this is all very nice, and it's a plot that we have seen more and more times, I think, in recent years, because, for example, the JWST is finding many new AGNs for which we are measuring the black hole masses at these very high redshifts, all still very uncertain, I think. But, for example, Euclid is also finding right now many of these new high redshift quasars. Roman will find many. And so, essentially, this plot will be more crowded in the near future, and we will be able to tell more about to play around with these growth histories. But I guess what I want to tell you is that every time you see a plot like this where there is this exponential line that goes down to the seed regime, we have to keep in mind that this is kind of close to nonsense, right? I mean, I think we can all agree that, assuming that the accretion of black holes is just exactly at the Eddington limit for the whole time is something that is extremely simplistic. And especially because we are exponentially sensitive to the growth rate, even changing a little bit our prescription on the accretion rate changes completely our conclusion, the conclusions that we can get about seeding. And all of this, I guess, is just to tell you the message that I want to tell you is that, I think we will never learn anything about black hole formation if we don't understand how black holes actually grow across cosmic time. And so if we kind of go beyond this extremely simplistic prescription of just Eddington limited accretion for the whole time. And how can we go beyond this prescription? Well, it's a hard problem, right? We can try to model it physically, for example, with an idealized simulation of what happens. And I think you know better than me that simulations of accretion of this kind all suggested that accretion is actually an extremely complex stochastic process that involves many orders of magnitude in terms of black hole growth rate, but also many orders of magnitude in time with different time scales that talk together in a very complex way. And so, but then when we go back to our modeling and when we try to play around with models, right, semi-analytic models, there's many different models that try to essentially picture this black hole accretion across cosmic time. We often just assume that quasars are just a non-off thing, right? And or we just assume some prescription for how quasar accretion may take place, but we completely neglect this large amount of stochasticity that is intrinsic to the to what we know about black hole accretion. And that is, I mean, there is a reason for that. And the reason is that we have no idea about how much stochasticity there is on quasars. I mean, we know quasars are stochastic because, I mean, in every band, whenever we see a quasar, we see it varying. And that is, of course, I mean, there is some stochasticity, and we know that this is well described by a stochastic process, but that is, of course, on human time scales, right? And so whenever we see quasar changes on the scales of years, we can just compute something that is like, for example, a power spectrum for these quasars, right? But then the point is that if we are really interested about black hole growth in a cosmological context, well, the timescales we're interested in are completely different, right? And we have no idea essentially how to extrapolate, how to go from this regime where we're actually measuring something about the stochasticity to the regime we're really interested in. So, I mean, yeah, it seems we're stuck. But I would argue that even if there's of course, no way to get direct information about the stochasticity of timescale of mega years, we can still try to get indirect information about this kind of stochasticity. And in particular, every model for stochasticity, every model for treating quasar accretion as a stochastic process here will need to be compatible with a whole set of observations that we have for quasars at a population level, right? Even if we don't have information of a single quasar, of how a single quasar varies, we still need to respect the fact that we have a lot of quasars in the universe, and we measure a lot of things about them. We measure their luminosities, and so, for example, we need to respect the luminosity function of these quasars across the entire cosmic time. We need to respect their black hole masses that we are measuring, and so the accretion history of these quasars needs to be to respect the fact that we're measuring different black hole masses at different cosmic time. We are measuring the clustering of these quasars, and the clustering is the way to essentially tie quasars to their cosmological context. And stochasticity changes a lot how quasars talk to the dark matter halos and to the cosmological context in which they're embedded in. And the last observables that we can consider is probably the most direct way to probe stochasticity, and that is the proximity, looking at the proximity region in quasar spectra, because the proximity region carries information about the imprint of quasars or the past quasars ionizing radiation on the surrounding IgM. And so essentially we can look at this proximity region and learn about quasar activity in the past few mega years. So we have all of these promising observables, and the idea that I kind of try to put forward in a sense is that we could try to use these observables to go beyond this modeling of a constant accretion across cosmic time, or the constant growth of volumetric luminosity and black hole mass for all the population that is treated in the same way, and really start probing, really try to start model accretion, so quasar activity and also black hole accretion as complex stochastic processes. Now, I decided to call this model BACARO, which stands for Black Hole Accretion and Quasar Activity in a Realistic Observational Framework. And since there is an overabundance of Italians here, the good Italians will be able to tell you that BACARO is just the name for a traditional wine bar in Venice. Let me give you a few details about this model. So we just want to essentially picture black hole growth to model black hole growth in a cosmological context. And so, like many other models do, we start with a large n-body simulation. And in particular, we did it very large because we really want to focus on the brightest quasars and most massive black holes that are there in the universe. And then we extract sub-halo merger trees from these simulations, and we try to tie to essentially paint the black hole growth on these sub-halo merger trees. And so we can make the physical assumption that the growth of each black hole is kind of tied to the growth of its host halo. But on top of that, we add stochasticity, and in particular, we add we treat this equation as a stochastic process, and we have some parameters controlling this stochastic process. And in particular, this will hopefully be able to capture these quasar accretion history, well, quasar radiating histories and black hole accretion histories in a realistic way. And of course, like the two, like the quasar activity and black hole accretion are of course tied to each other once we select the radiative efficiency, right? So every time we talk about black holes, we can talk about quasars and vice versa. Now, let me give you a few more details about how this works in practice. And so this is an example of a merger tree for these subhalos. And you see that the first thing we need to do is every time we identify a halo in the simulation, we need to put a black hole there. So I'm calling this process seeding. We have two free parameters for determining how to put black holes whenever halos spawn in the simulation. But of course, like the resolution of the simulation is not good enough to go down to the halos, which are supposed to be the actual host of the real seed black holes. What we are doing is more like kick-starting empirically this black hole mass halo mass relation at the bottom left, so for the very low mass halos in the simulation. And then, like these both black holes and halos will grow across this relation, right? And they will grow in two different ways. One is by merger, and we can just follow along the merger tree of halos. We can just follow that for the black holes as well. And the other one will be via accretion, right? And the accretion, as I mentioned, we try to tie together the accretion of black holes to the accretion of halos. And in particular, we are tying together the Eddington rate of black holes to this cold specific halo accretion rate, which is essentially the accretion rate multiplied by a parameter that determines what is the mass in the amount of mass which is available in cold gas. And you see that this quantity is a very strong function of redshift. This is a very simple, result from cosmology. And since this quantity is a very strong function of redshift, black hole accretion will also be a very strong function of redshift, and we can look at the consequences of this later. But then we have stochasticity on top of this. And so for the stochasticity takes two forms. One is that for every black hole halo pair, essentially, there is the black hole won't follow the halo directly one-to-one, but there will be some global stochasticity that will be able to determine how essentially the black holes depart from the halo growth. And this global stochasticity is also accompanied by this kind of burstiness parameter, which is really carrying the information about this power spectral density of this stochastic process, right? And in particular, we are modeling this in the most simple way possible, which is just assuming some coherence timescale for this process. And I'm calling this burstiness just because, I mean, a large coherence timescale of, for example, 10 megayear implies that this accretion rate, the accretion happens in a long burst of coherent structures. Whereas, like, if we go down to very short coherence timescales of like 0.1 megayear, for example, the resulting radiative history for the quasar will be extremely bursty and extremely stochastic and rapidly varying. So this is kind of the overall picture of the model. And just to sum up, we have then like a bunch of free parameters, 6 free parameters. And for every combination of the parameters, we can just determine a merger history for the black holes. And for each of the black holes that we have in the simulation, we can essentially determine their quasar activity across the entire cosmic time and the build-up of black hole mass. Once we have that, well, we can try to compare the data. And in particular, we need to build emulators for each of the observables we are considering. And once we have the emulators that are essentially predicting how the model looks like for every combination of parameters, how it looks like in terms of observables, we can do inference and determine what is the combination of parameters that matches observations. And then considering several observables, for example, the luminosity function, the clustering of quasars, and some information on the Eddington ratio, that we are measuring from these quasars. And you see that like we can answer questions like what is the constraining power of the luminosity function of quasars taken across the entire cosmic time in determining what is the connection between black holes and dark matter halos, in determining how this connection is actually stochastic, and in determining like how to essentially kickstart this relation through this seeding process. The first thing I want to convince you about then is that like we are matching the data. This combination of parameters, like the ones that are like found by our inference, is matching the data really well. And you can see here an example of this is the bolometric luminosity function. So it's a luminosity function created by putting together all the data from different bands like X-rays, UV, UV optical, mid-infrared, and so on. And the idea is that, like, of course, we're also correcting for obscuration, and like the luminosity function itself is also correcting for obscuration and everything. So it's meant to capture really the entire activity of quasars, and so we can just compare it directly to the output of our model. And you see that we match pretty well the entire evolution of this luminosity function across cosmic time. Of course, we are fitting to match these, so it's kind of no surprise, but it's also non-trivial that we are matching it across the entire cosmic time, right? Because we only have 6 parameters, and none of our parameters are essentially telling us anything about redshift. The only thing that our parameters are telling us is how a black hole talks to its own halo, and not and the fact that we don't have to put very complex prescriptions that change completely the way accretion takes place at high redshifts is already telling us something about the fact that accretion in the universe maybe has a simple physical, can be understood via simple prescriptions, right? This is another way to actually see this rise of luminosity, the luminosity of quasars and the downfall, like the peak at cosmic noon and the downfall at lower redshifts. You may notice that we are a bit overshooting the faint regime, but I think like for the faint quasars, I think we are learning more and more that we need to be careful when we consider the faint quasars, because we don't know really well how to what is the real abundance of these faint quasars, and especially what is the real obscuration fraction for these faint quasars. I think from X-rays, from mid-infrared studies now, we are learning that the obscuration fraction might be larger, and so if the obscuration fraction is larger, we need to essentially bring our model up and try to match this data as well. The second observable is the clustering, and I just go to the data, and the idea is that like we're also considering here the clustering, just a subset of all the clustering measurements that are out there. In particular, we are considering SDSS, so UV optical clustering, and JWST clustering at very high redshifts. And I think we are matching the clustering pretty well. There is like this disagreement at redshift 4, but this is like a very well known, and I mean, I think this is very much expected. So you can ask me more if you're interested, but I think this is fine and expected from the model. And the last quantity we're looking at is essentially Eddington rate. So we're looking at the Eddington rate distribution as a function of redshift and of different luminosity beams. And we're comparing the model, so the solid line, with the data that are being histogram. And we're kind of reproducing it relatively well. We can discuss about the details if you're interested, but I do want to jump to the results. And the first thing we can look at in terms of results is the quantity that we didn't fit for example, and this is the local black hole mass function. So the shape of the black hole mass function in the local universe, which is which is also supposed to be a direct observables, is surprisingly not very well constrained at the very massive end. But that is also interesting because for example, what we find in our model is that the very massive end of the black hole mass function in the local universe is essentially where mergers, like black hole mergers, start to be very important and start to change the shape of the black hole mass function a lot. And the idea is that the fact that mergers matter a lot here is very interesting, right? Because of course, the massive end of the black hole mass function is directly connected to the gravitational, is exactly what determines the gravitational wave background that is measured by the pulsar timing arrays observatories, right? So I did the exercise of predicting what the model would look like if compared to PTA. And then we are like a little bit lower, which I mean, I think it was partly expected, and there is a large literature on how to connect the black hole mass function to the PTA signal. But I think the interesting part is that like merger can drive directly the signal, but also drive the massive end of the mass function in the model. And so essentially the idea is that it would be interesting to essentially put PTA constraints directly in this corner plot and talk about the constraining power of PTA constraints and of gravitational wave mergers as well, along with the constraints that we like from proximity zones, right? Because the proximity zone are also not considered yet in the model, not in terms of inference. But I think it's like kind of reassuring that the coherence timescale that we're getting is around 1 mega-year, which is perfectly compatible with the coherence timescale measured by, well, the lifetime measured by proximity zones across the history of the universe. The last two things I want to mention very quickly, where one is about the black hole mass-halo mass relation, and in particular, one thing I would be interested in is understand how this relation is shaped by accretion and is shaped by mergers. And you see that like mergers do have a very large impact in shaping this relation. And in particular, I think the relation is kind of stable across redshift. It doesn't change much across redshift, but the scatter on this relation is changed a lot across redshift. And the scatter is changed mainly by mergers. And in particular, mergers decrease the scatter in this relation a lot to the very massive end for very massive halos, and they decrease the scatter at lower redshift. And there is like there are connections that we can discuss about, for example, the overmassive problem for black holes that are found by JWST. But I wanna jump to the final slide, which is circling back to the highest redshifts, right? And in particular, is going back to the problem of how do we grow these 10 to the 9 solar mass black holes in the universe at redshift 6 and 7. And I'm taking here a representative example. But like, the thing the question I want to answer is how this model presents a solution that like has a stochastic history, which is kind of realistic, but also can go this 10 to the 9 solar mass black holes at redshift 6 and 7 essentially. And the idea is that like the halo growth rate becomes so large at high redshift that super-Eddington accretion becomes natural in the model. And in particular, this super-Eddington accretion is also extremely stochastic. So the median is not very, very much above the Eddington limit. But there are these long bursts of super-Eddington, which last around 1 mega-year. And that is our constraining power in terms of this 1 mega-year. Like that essentially these long bursts are enough to actually build these very massive black holes. But at the same time, then there are like these dips below Eddington that like that essentially make it so that black holes don't grow too massive. And essentially, this 1 mega-year is found as a constraint between like the fact that these black holes need to grow very, like the accretion needs to be coherent enough for these black holes to grow enough, but they also don't need to grow too much and overgrow essentially at lower redshifts. So this is where our constraining power is coming from, I think. And with this, I leave you a low overview summary, and I'm out of time, so I'm happy to take any questions. Thank you.
We have time for one question because there's people coming in for 1:30. But actually, Elia is here.
So very interesting. Your goal was to learn about how black holes form. But during the simulation, your first step was to actually put a black hole seed there. So what was the mass of the black hole seed, and how will your results change if you apply different black hole seeds?
Yeah. So the seeding is so what we are parameterizing is essentially we are finding that the seed needs to be around 10 to the minus 5. So 10 to the 5.6 times smaller than the halo, which means seeds around 10 to the 5 to 10 to the 6. But you need to take into account that the resolution of the simulation is not good enough to go lower. So if we extrapolate and go to lower masses, you could find seeds that are much lower in principle, of much lower mass in principle. So the idea is like we do need to find a way to, if we want to talk about seeding, we do find that there are constraints. The model is indeed able to constrain the fact that there is like we have some constraining power on the seeding part, but we don't have the resolution to go down enough to talk about real seeds. I think this constraining power though comes from the fact that we are assuming that the accretion is to be the same at all cosmic times. And so essentially this is like enough to kind of break the degeneracy between very, very, very fast accretion at high redshift or massive seeds, right? Because like, I mean, okay, we can talk about this more, but the point is I think we have some constraining power to break this degeneracy, but we would need a bigger simulation to go down to the actual physical seeds. Or, well, some way to extend the problem.
But you assume like a single mass seed.
No, a distribution.
Distribution.
Yeah, with like with this cutter.
Okay.
Yeah.
Okay, I'm afraid we're out of time, so let's thank Elia again. Yeah, so if you do have more questions for Elia or Roberta, please get in touch, but unfortunately, we need to leave the brain. So see you next week.
You have time.
Maybe